Right, hello students. Today we're going to be doing sequences and series, arithmetic sequences and partial sums. Okay, so let's go ahead and start talking about the sequences. So, in mathematics, the word itself, sequences, is used as the same way as in English. Essentially, it's going to be a collection in a certain order, so that the first member, we have a second member, we have a third member, so on and so forth. Right, so but in mathematics, we also explore the concept of infinity sequences. Right, we can be infinite. So an infinite sequence is a function whose domain is the set of positive integers. So the function values a1, a2, a3, an, are the terms of the sequence when the domain of the function consists of the first n positive integers only. The sequence is finite sequence. Okay, so first example, let's go ahead and try to find following. So example 1. So let's say, let's write down first four terms of the sequence. So a sub n is equal to 3n minus 2. Okay, so that means, well, we want to find first four terms. Okay, so that means a sub 1 is going to be 3 times 1 minus 2, which is equal to 1. Then a sub 2 is going to be 3 times 2 minus 2, which is equal to 4. A sub 3 is going to be 3 times 3 minus 2, which is equal to 7. And then a sub 4 is going to be equal to 3 times 4 minus 2 is equal to 10. Okay, so this is first four terms of this sequence. Right, how about if we do the same thing, but for a sub n being equal to 3 plus negative 1 to the power of n. Right? How will we solve this? Well, once again, a sub 1 is equal to 3 plus negative 1 to the power of 1. So that would be 3 plus negative 1, which is equal to 3 minus 1, which is equal to 2. How about a sub 2? It would be 3 plus negative 1 squared is equal to 3 plus 1, which is equal to 1 is equal to 4. Okay, now we can repeat the process. So a sub 3. 3 plus negative cube, so that's equal to 3 plus negative 1, which is equal to 3 minus 1, equal to 2. And then a sub 4 plus negative 1 to the 4 is going to be equal to 3 plus 1 is equal to 4. Alright, so this one is repeating sequence. Alright, so of course we can get a more and more complicated one. Of course, I'll try this one on your own. So example 3, a sub n is equal to negative 1 to the power of n divided by 2n plus 1. Okay, so the terms for the sequence are going to be as following. So a sub 1 is equal to negative 1 to the power of 1 over 2 times 1 plus 1, which is equal to negative 1 over 2 plus 1, which is equal to negative 1/3. Okay, how about a sub 2? Which is equal to negative 1 to the power of 2. 2 times 2 plus 1, which is equal to 1 over 4 plus 1, which is equal to 1/5. Then a3. Negative 1 to the power of 3. 2 times 3 plus 1, which is equal to negative 1 over 6 plus 1, which is equal to negative 1 over 7. And then a sub 4 is going to be negative 1 to the power of 4. 2 times 4 plus 1, that's equal to 1 over 8 plus 1, which is equal to 1 over 9. Okay, so, but sometimes, right, sometimes what do we want to do? We want to be able to find the pattern, right? Sometimes we need to be able to recognize the pattern. So, now, let's go ahead and try to find pattern, right? So, let's see. I'm going to say example 4. So for finding patterns, let's say we have a sequence, a basic sequence. 1, 3, 5, 7, 9, 11, 13, 15, ... Okay? Right, this is the first few terms of the sequence. And so I want to find a pattern. Right, but clearly we have, if we start with n, right, a sub n, if we start 2n, right, 1 is going to be 2, is going to be 4, 6, then 8, then 10, then 12, 14. So, but here they are all minus 1. So if we subtract minus 1, we actually will get a sub 1 is equal to 2 times 1 minus 1 is equal to 1. A sub 2 is 2 times 2 minus 1 is equal to 4 minus 1 is equal to 3. A sub 3 is equal to 2 times 3 minus 1, which is equal to 6 minus 1, which is equal to 5, etc. Right, so that's going to be our formula. So sometimes we might be given a pattern, right? We might be given a pattern, but sometimes patterns are not as obvious, right? They are not as obvious. So sometimes we have to take some time to find it. So an example. So let's say we have 2, negative 5, and negative 17, etc. Right? What can we find it as a pattern? So it turns out we can find a pattern. And that pattern, well, first of all, it's switching signs, right? So if it's negative 1 to the power of n plus 1 times, so what do we have here? What do we have here? If we have 1, we get a 2. If we get 2, we get a negative 5. So what if n squared plus 1? So 1 squared, that's 1, plus 1, that's 2. And here it's positive, okay? So let's check it out. So a sub 1, negative 1 to the power of 2, 1 squared plus 1, which is equal to 1 times 2, which is equal to 2. Okay, now how about the second term? So the second term is going to be the following. So a sub 2 is equal to negative 1 to the power of 3, 2 squared plus 1. So that's equal to negative 5. How about the third term? It's going to be negative 1 to the power of 4, 3 squared plus 1, which is equal to 10. And the fourth term, so a to the fourth, it's going to be negative 1 to the power of 5, 4 squared plus 1 is equal to negative 17. All right, perfect. So, all right, so sometimes we do need to find some of the sequences, like, and we can also have a recursive kind of sequence, right? So a recursive kind of sequence is going to be as following. So example 6, the recursive sequence is, let's write it down. It depends on its previous input, right? So recursive is, well, let's say a sub 1 is equal to 3, but a sub k is equal to 2 times a sub k minus 1 plus 1. Right, and k in this case is greater or equal to 2. Right, because a sub 1, when k is equal to 1, we already have. So that kind of sequences are used in computer science and programming to solve equations. They are very, very useful. So, okay, so for the recursive function, so let's check it out. So a sub 1, we know that it's equal to 4. A sub 2 is going to be 2 a sub 2 minus 1 plus 1, which is equal to 2 times a sub 1, 1, which is equal to 2 times 3 plus 1, which is equal to 7. Okay, now repeat the process. So a sub 3 is equal to 2 times a sub 3 minus 1 plus 1, which is equal to 2 times a sub 2 plus 1, which is equal to 2 times 7 plus 1, which is equal to 15. Then a sub 4 is equal to 2 times a sub 3, 1, is equal to 2 times 15 plus 1, which is equal to 51. And let's do last term. So a sub 5 is going to be 2 times a sub 4 plus 1, which is equal to 2 times 51 plus 1, which is equal to 63. Okay, so that's one of the recursive ones. And of course, one of the famous recursive sequences that we can have is a Fibonacci sequence, right? And essentially, one of the most famous ones, the Fibonacci sequence. So I'm going to say that a sub naught is equal to 1, and a sub 1 is equal to 1, and a sub k is equal to a sub k minus 2 plus a sub k minus 1, where k is greater or equal to 2. Okay, so we're starting here at 0. We just shifted it one unit to the left, which is fine. So, okay, so let's write down our list. So a sub 0 is 1, a sub 1 is going to be 1, then a sub 2 is going to be a sub 0 plus a sub 1, which is equal to 1 plus 1, which is equal to 2. How about a sub 3? It's going to be a sub 1 plus a sub 2, which is equal to 1 plus 2, which is equal to 3. a sub 4 is going to be a sub 2 plus a sub 3, which is equal to 2 plus 3, which is equal to 5. And then a sub 5 is going to be a sub 3 plus a sub 4, which is equal to 3 plus 5, which is equal to 8, and etc. Right? We can continue that infinity, but that's essentially how we're using the recursive formula. Okay, now one of the important subjects for sequences and for series in general, it's called a factorial. So, a factorial, let's go ahead and give a definition of a factorial. Very special function. So, if n is a positive integer, then n factorial is defined as n with the exclamation mark is equal to 1 times 2 times 3 times 4 n minus 1 times n. Okay, in a special case of 0 factorial is defined as factorial of 0 is equal to 1. It's a very interesting function. A very interesting function, and we're not going to go in details too much in it because it's more you learn more about it in calculus. But it has some properties, some interesting properties. So n factorial is equal to n times n minus 1 factorial. Remember, you can also write it as n times n minus 1 times n minus 2 factorial, and that factorial applies only to the last term, right? So this factorial applies to this term, this factorial only applies to this term, right? And that makes sense because, well, 7 factorial, we can write it as 7 times 6 factorial, right? Because by definition, it's just multiplication, and that's going to be the same thing as 7 times 6 times 5 factorial. And then we can continue that until we get 7 times 6 times 5 times 4 times 3 times 1. Right, that's one of the very important properties of the factorial. And we will be using it later in the next lesson for probabilities. So, but now, we have a small introduction of it. We're not going to have too much examples on it. Let's go ahead and actually take a look at, one more important note for factorials. They are different. So, if you're trying to do 2n factorial, that is going to be the same thing as 2n factorial, which is 2 times 1 plus 1 times 2 times 3 times times n, right? And it's not the same thing as 2n factorial, because 2n factorial would be essentially going for the 2n components, right? It would be 1 times 2 times 3 times 4 times 2n. And we would be, when we take it out, we would take it out as 2n times 2n minus 1 factorial. N minus 1 like this. N minus 2n minus 1 factorial, right? We're subtracting as a whole thing. So, okay. Right, and then we can also write it as 2n times 2n minus 1 times 2n minus 2 factorial. Okay, perfect. So now, let's go ahead and move on to the summation part. Because we talked about sequences, we talked about factorials, we practiced some sequences. Now, let's define a summation. So, a sum of first n terms of a sequence is represented by the following notation, right? This is a capital sigma. This is how we write it. It represents a sum, right? A sum of an element a sub I, which is written as a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 all the way to a sub n. Okay, where I is the index of summation, n is the upper limit, right? N is the upper limit right here. It's an upper limit. And 1 is the lower limit. So 1 right here, we're starting from 1, ending at n. Okay? So let's go ahead and take a look at the example here. Example 2.1. So if we say, well, the sum for I equal to 1 up to 5 of 3 times I. Okay? So that would be 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. So that's equal to, we could factor out the 3. It's going to be 1 plus 2 plus 3 plus 4 plus 5, which is equal to 3 times 15, which is equal to 45. Okay, and of course, we don't always have to write I. Sometimes we can write K, right? That's also a common thing. So another example would be, so it's example 2. So it would be the sum for k equal to 1 up to 6 terms. Sure, no, let's do it actually, not from 1, let's do it from 3 up to 6 terms. So we're going to have 1 plus k squared is going to be equal to 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1 plus 6 squared. Okay, so that would be equal to, so that's 9, 16, 25, 56. So add 1 to everything is going to be 10 plus 17, 26 plus 57, and that would be equal to 90. Okay, perfect. So now a series, right? This was a summation. Now let's go ahead and define series, because series are essentially related to the sum. So now consider an infinite sequence, right? So the sequence doesn't have an end, essentially. The sum of the first n terms of the sequence is called a finite series of the nth partial sum of the sequence, and is denoted as the following, right? That's what we did previously as the summation. Okay, then the sum of all terms of the infinite sequence is called an infinite series, and is denoted as this. So now we have an infinite amount of components. So that is going to be useful, right? That is useful for computing some things in mathematics, and specifically calculators. Calculators use those techniques. We don't use infinity, of course, because infinity is a mathematical concept. Just calculators use very, very high numbers, right, instead of n. So the higher the number, the more accurate the representation is. Okay, so this is essentially the definition of series. And one more thing, let's talk about a general. Like in general, what are the properties of sums in series, right? So the properties, alongside with the definition, is as following. So we can have the sum, right? The sum of the following. So the sum of c of a constant is just going to be the sum of numbers, right? Up to so it's c times n. So if n, let's say, is infinity, then that sequence does not have a sum, because you infinitely amount of times adding the constant. So for number 2, we can take out a constant, right? We can factor it out, essentially, out of the sum. Then for this one, we can separate the summation sign and have 2 different summations. And same thing for subtraction. Okay, now what we can have is we can have an interesting infinite series, right? So let's go ahead and take a look at some infinite series examples. So, example 3.1. So that would be, so let's say we have a series of I equal to 1 all the way up to 3, right? And that's going to be equal of the following. It's going to be 3 over 10 to the power of I, right? Let's say that. So then we're going to have 3 over 10 plus 3 over 10 squared plus 3 over 10, right? And that's going to be equal to 0.3 plus 0, 0, plus 0, 0, 3, which is equal to 0, 3, 3, 3. Okay, now let's say we're going to do same thing, but now instead of 3 terms, we're going to have infinite amount, right? So for infinite amount of terms, 3 over 10 to the I, well, it's going to be, as you can imagine, 3 over 10 plus, well, 3 over 10 squared, that was 3 over 100 plus 3 over 1,000 plus 3 over 10,000 plus etc., right, until essentially infinity. So what are we going to end up getting is 0.3 plus 0.3 plus 0.03 plus 0.0003 plus smaller and smaller and smaller. So essentially we're going to have repeating 0.33, right? This means repeating. So that's essentially equal to 1/3. Okay, that is equal to 1/3. So essentially, sometimes sequences will give us exact numbers here. So one of the applications of series, let's actually take a look at it, specifically for compound interest. So here we will have as following. So an investor deposits $5,000 in an account that earns 3% interest, compounded quarterly. The balance is in terms. The balance in the account after n quarters is given by the following equation. write the first three terms of the sequence. Okay, so let's go ahead and do that. So step A, part A essentially is going to be A sub 0 is equal to 5,000 times 1 plus 0.04 to the power of 0. So that's equal to, so that's 1. The whole thing becomes just 1. So because it's to the power of 0, it's just going to be 5,000. Then A sub 1 is equal to 5,000 times 1 plus 0.03 over 4 to the power of 1. So that's going to be equal to, by using calculator, we get 5,037.5. Okay. And then A sub 2 is going to be equal to 5,000 times 1 plus 0.03 divided by 4 squared. That's going to give us 5,075.28. So now, let's go ahead and do part B. We want to find the balance in the account after 10 years by computing the 40th term of the sequence. So essentially, we have to do A of 40 is equal to 5,000 times 1 plus 0.03 over 4 to the power of 40. So by using calculator, we're going to get $6,741.74. This is going to be the 10-year balance. All right, perfect. So that was essentially what the sequences in series are. Now, let's go ahead and dive into more specific sequences in series. So we're going to start with the arithmetic sequences. Right. So this lesson is going to be about arithmetic sequences, and next lesson we're going to do geometric ones. So we're going to start with arithmetic. So arithmetic are going to be referencing essentially, we also known as algebraic sequences, so we're going to be mentioning addition and sometimes some sort of multiplication involved, right? So arithmetic sequences. So by definition, we're going to have that a sequence is arithmetic when the differences between the two consecutive terms are the same. So the sequence A1, A2, A3, A4, all the way to AN, etc. is arithmetic when there is a number D such that A2 minus A1 is equal to A3 minus A2, A4 minus A3, all the way, etc. is equal to D. So the number D is the common difference of the arithmetic sequence. Right, and I showed you some of the sequences previously, like 2n minus 1, right? We all had a difference of -1. So essentially, here, we will have, let's say we take a look at, for example, 3.1. So we had a sub n is equal to 4n plus 3, right? So starting for a sub 1 is equal to 7, a sub 2 is going to be equal to 11, a sub 3 is going to be equal to 15, right? And then at a sub 4 is going to be equal to 19. So a sub 2 minus a sub 1 is equal to 4. A sub 3 minus a sub 2 is equal to 4. A sub 4 minus a sub 3 is equal to 4, etc. So in this case, the D term, right, is equal to 4. Difference between them is 4. Okay, so essentially, the general formula, right, the general formula for the sequence is as following. So we're going to have a sub 1 is equal to 1, then a sub 2 is equal to a sub 1 plus D. A sub 3 is going to be a sub 1 plus D, which is equal to a sub 2D. Right, then a sub 4 is going to be a sub 1 plus 3D. And then a sub 5 is going to be 1 plus 4D, right, etc. So that means that a sub n is equal to a sub 1 plus n minus 1 times, right? That's going to be the nth term arithmetic sequence. Okay, so that's going to be the formula for it. Perfect. So now I'll write it down neatly here on the side. So, okay, the nth term of the arithmetic sequence has the following form. A sub n is equal to a sub 1 plus n minus 1 times d, where d is the common difference between consecutive terms of the sequence, and a is the very first term of. Okay, perfect. So that also is very helpful for the recursive formulas. Okay, and you can go back to the examples that I showed at the beginning and use it to actually develop the sequences. Right? And that's how you would develop a sequence. If you were given one, you can first check always if it's arithmetic sequence or not. Okay, and now let's go ahead and use that fact to do the sum of the finite arithmetic sequences. So if we want to sum up the sequences, right, we want to find the sum. So the sum of the arithmetic sequences with n terms is given by s sub n is equal to n over 2 times a sub n plus a sub n, right? So the first term of the sequence plus the last term of the sequence divided by 2 and multiplied by the total number of terms in the sequence. Okay, so that problem or that formula was created by Gauss. So Gauss was very, very clever. He essentially developed that formula because he was posed a question of as following. So example 3.2. So he wanted to add all of the terms, right? 1 plus 2 plus 3 plus 4 plus dot 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 plus 100, right? All the way to 100. From 1 to 100, he had to add the terms. Okay, so essentially he was able to find the equation and prove it. General equation for arithmetic sequences. So essentially, by using that formula, so s sub n is going to be equal to 100 over 2, because we have 100 terms, times 1 plus 100. So that's equal to 50 times 101, which is equal to 5050. Right, so when you add the first 100 numbers from 1 to 100, your total sum is going to be 5050. Okay, this is one of the very famous examples of the partial sum. And of course, let's take a look at one more example. Example 3.3. So if we have 100, 95, 90, 85, 80, that. So, right, our first term is 100. Our difference term is going to be, let's do a2 minus a1, which is equal to 95 minus 100, which is equal to negative 5. Okay, so they're all different by 5. So our a sub n is going to be what? 100 minus 5 n times negative 1. Okay, and of course we can also use the sum. Right now, since we're given that, we can find any of the numbers and any sums. And we can use the formula for the partial sum to find it. All right. So let's see. Let's see some of the applicational examples. So that would be an applicational example for a small business here. So a small business sells $10,000 worth of skincare products during its first year. The owner of the business has set a goal of increasing annual sales by $7,500 each year for 9 years. Assuming that this goal is met, find the total sales during the first 10 years the business is in operation. So, right, essentially we can think about a graph. Right, but first let's think that we're given a sub 1 is equal to $10,000, and then the difference here is actually 7,500. And n is going to be number of years, right? So our formula is going to be a sub n is equal to 10,000 plus 7,500 times n minus 1, right? So we can use that to graph it. Okay, so we're going to get a linear graph here of our sequence. So the 10th term, what would be the 10th term? So a sub 10 is going to be equal to following. So, and we can also, we can rewrite that as, if we distributed 7,500 n plus 2,500. Okay, so a sub 10 is going to be 7,500 times 10 plus 2,500, which will give us $77,500. Okay, now we wanted to find the sum, right? Assuming that goal is met with the total sales during those 10 years. So, S sub 10 is equal to, so we're going to do n over 2 times a sub 1 plus a sub n. So in this case, a sub n is going to be 10. So, we're going to say, okay, so first 10 years over 2, a sub 1 is 10,000 plus 77,500. That's equal to 5 times 87,500 is equal to $457,500. That is the total number of sales during the first year. All right, perfect. So for the next lesson, we're going to continue some of the serious applications and also the geometric sequences. Thank you, students, and see you next time.